Hi everyone, my name is Marius, and today I'm going to present to you our work on R2P2, a transport protocol for data center RPCs. This is work done with my colleagues George, Adrien, and George, and Jonas, and our advisor at Bugnion in EPFL. So, if you take a look inside the modern data center, more or less you will see something like the following. The networking infrastructure is organized in a closed topology with links of 10, 40, or even 100 gigs, and typical round-trip times are just a handful of microseconds. Also, in-network programmability becomes more and more commonplace with programming languages such as P4, programmable switches, and routers. So on top of this infrastructure, we have applications such as data stores or web search that communicate in complex fan-in and fan-out patterns under strict service-level objectives for their tail latency. The base of this communication is remote procedure calls that can have various service times. In this talk, we will focus on microsecond scale RPCs, and we will see how we can deliver them and schedule them inside the data center. So a common design pattern is to multiplex RPCs on top of a reliable byte stream protocol such as TCP. So TCP makes sure that packets are delivered in order, P1, P2, P3, and these packets can carry either entire requests, such as R1 and R2, or partial requests, such as R3. However, the mismatch between those two abstractions can cause several issues. And in this talk, we will focus on two of them. The first one is ordering and head-of-line blocking. So TCP orders requests that are delivered on top of the same connection, despite the fact that RPCs are independent and they can be served independently. So in this case, the long R1 request that can also take longer to be served will delay the shorter R2 and R3 requests. Also, losing packets only makes things worse, because then the TCP mechanisms will kick in and try to recover the lost packet. At the same time, the network is RPC agnostic when we deliver RPCs on top of TCP. And this is because TCP hides the RPC semantics. So in this particular case, you can see the RPC boundaries for R2 and R4 are not aligned with the packet boundaries. So whenever we want to implement some kind of policy, the middle boxes have to either do deep packet inspection, or they have to terminate client connections and open new connections to the servers. So in this talk, we will focus on this mismatch, and we design R2P2, a transport protocol specifically for RPCs that exposes the RPC abstraction to the network and enables a network policy enforcement. Using this new abstraction, we implement efficient in-network RPC load balancing. So we introduce R2P2, a request response pair protocol. R2P2 is a UDP-based connectionless protocol that exposes the abstraction of a request and response pair. So R2P2 does not implement connections or individual messages. Also, these request and response pairs are independent, so there is no protocol-enforced ordering. One client can have several outstanding requests, so here the blue and the orange one, and the replies can come back in any order. The other thing is that with R2P2, we don't have fate sharing. So losing a packet will only affect the equivalent request and response pair. So in this case, if we lose the blue packet, the orange reply can come back without any issues. Finally, by doing that, we allow clients to make per RPC-specific decisions, so they can decide for timeout timers or change between at least once and at most once RPC semantics. In R2P2, each request and response pair is only identified by the source port and IP and a request ID set by the client. By doing that, we can break the traditional point-to-point RPC semantics. So since the request destination can be different than the reply source, clients can receive replies from servers that are different than the ones they initially sent the request to. Also, this allows us to make per request decisions regarding placement and scheduling. So by exposing these independent request and response pairs, R2P2 deals with the problem of ordering and head-of-line blocking. Then let's take a closer look at a packet exchange for an RPC on top of R2P2. Imagine that we have a client and a bunch of servers, and in between there is a middle box that implements some RPC policy. So initially, the client sends the first packet to the middle box, rec0, and this packet can either carry the entire request if we're talking about a single packet request, or just a part of the request. Then the middlebox makes a decision and chooses a target server. And in the case of a multi-packet request, the server notifies the client that is ready to serve this request, and the client serves the rest of the request to the server by passing the middlebox. Then the server serves the request and streams the reply back to the client, again by passing the middlebox. Finally, R2P2 implements application-specific feedback messages from the servers to the middlebox. So what we see here is that by exposing the RPC abstraction to the network, we have request and response aware middleboxes that can implement in-network policy enforcement at line rate. Also, with this design, the middlebox only participates in the policy enforcement and not in the request and reply streaming. And as a result, this is not an I/O bottleneck. So by exposing this RPC abstraction to the network, we make the network RPC aware, and we can claim that RPCs are first-class citizens now. So once we established this abstraction, we started thinking, what can we do with this? And the first use case that came in mind is request-level load balancing. So let's take a look. What can we do with request? How can we do request-level load balancing with existing technologies? So what you could do today is you could deploy something like a reverse proxy, NGINX, or Envoy, etc. And this reverse proxy would have to terminate client connections and open other connections to the server. So we deployed this system. So we have 4 backend servers that run a synthetic service time with 25 microsecond service and that comes from an exponential distribution. And we put those servers behind an NGINX reverse proxy, configured it with the join shortest queue policy. And as we can see here, despite the fact that the optimal throughput that we could get is almost 2.5 million requests per second, we cannot go above 200,000 requests. And this is because NGINX is an I/O bottleneck in this case. So this is what we did. We implemented R2P2 middleboxes. One is software, specifically on top of TPDK, that only adds 5 microsecond end-to-end latency overhead, and it can saturate a 10 gig link with 2 CPU cores, and one that runs on top of a Tofino barefoot ASIC that only adds 1 microsecond latency overhead. And we configured these routers to forward requests with the simplest policy, which is random. And as we can see here with the pink curve, we can get significantly throughput benefits compared to the case of NGINX. So can we claim victory? Yes, we can. But the question is, can we do better than that? And fast forward, we can even do better than that. So we built a system that can actually deliver the gray line. And let's take a look at how we got there. But first, let's step back and look at a closer look at load balancing and try to understand what's going on. So there are 2 main design patterns regarding load balancing. In the first one, we have distributed queuing. So the dispatcher forwards requests to the servers, and each server has its own queue. The simplest policy to forward request is just random, and in this case, we're talking about n independent MG1 systems. On the other hand, we have centralized queuing, where a central dispatcher, where all the requests get queued up in the central dispatcher, and then servers pull from this dispatcher. So in this case, we're talking about an MGN system. And from queuing theory, we know that the performance difference between those 2 systems is clear. And because the distributed queuing suffers from transient load imbalances, the centralized queuing models perform way better in terms of tail latency. However, when we talk about scalability, the story is different. So distributed queuing scales way better because you can see this as equivalent to layer 4 load balancing, while a single queue system exposes the communication overhead and does not scale that well. So the question we ask and we are trying to answer is, can we implement RPC load balancing across multiple servers with single queue-like performance while we can scale throughput and achieve low latency? And to do that, we introduce a new scheduling policy, which is joint bounded shortest queue, or JBSQ for shorter. So JBSQ is a split queue model that splits queuing between a central part, which is unbounded, and several bounded queues, 1 per server. So in this case, the bounded queue has a size of 2. The idea here is that whenever the bounded queues are full, requests will get queued up in the central part. And the rationale behind this policy is to delay the scheduling decision as much as possible in anticipation of better placement. There is an obvious trade-off here between throughput and tail latency. We can increase the number of n so that we can get more throughput, but this can lead to bad placement and worse tail latency. If we reduce n, we can improve tail latency, but at the same time, we expose the communication delay between the central queue and the bounded queues, and this does not allow throughput to scale. So now let's see how we can implement JBSQ on top of R2P2. And for that, we will bring back the packet exchange that we saw before. So we put the central queue at the middle box where the rec zeros get queued up, and we have bounded queues 1 per server. The middle box maintains the number of outstanding RPCs per server, and then we use the feedback messages from the servers to the middle box to signal the termination of each RPC. So now the question is, how much better is JBSQ compared to the random policy that we saw before? And we ran the same experiment, but now because we do not have the IO bottleneck, we can go even lower in terms of service time. So now we deploy the same 4 servers, but with an average service time of 10 microseconds. And we plot the random policy that we saw before, and we also plot the single queue model as we get the results from a discrete event simulator. And this is the theoretically optimal model result that we can get. So first, we deploy our systems, our software approach with 1 outstanding request. And here we can make 2 observations. The first one is that we achieve lower tail latency, so we're closer to the central queue model, but we cannot scale throughput because there is not enough concurrency. So let's increase the number of outstanding requests. We increase the number of outstanding requests to 5, and what we see here is that we can get the maximum throughput as it's predicted by queuing theory under the tail latency SLO. Then we also deploy our hardware approach based on P4. And because the performance difference between the software and hardware approach, again, here we can make 2 observations. The first one is that we need less outstanding requests per server because the communication overhead is lower. So with 3 outstanding requests here, we can get the same maximum throughput. The next observation we can make is about the impact of the number of outstanding requests to tail latency. So a lower number of n leads to better tail latency results because we can make better placement decisions, and you can see the difference between the 2 curves. OK, so far, I've only talked about load balancing. And the question that you might ask now is, what kind of other policies can we implement on top of R2P2? So R2P2 supports any kind of application-specific policy and can be extended with new ones. So in the R2P2 header, we have specifically 1 policy field that can be interpreted by the router based on the policy that we would like to implement. Specifically, we only implemented 2 policies, route any and route fixed. So in route any, the middle box is able to choose any of the target servers, while in route fixed, the middle box has to forward the request to 1 specific predetermined target. Ideas for alternative policies are sticky, so that we can implement some kind of sticky consistency where requests from certain clients only go to certain servers, or hashing in order to implement some kind of sharding where the middle box can hash parts of the request and forward the request to the equivalent server. So we used this policy field in our next experiment based on Redis. So Redis is an in-memory key value store that supports master-slave replication. And in this scheme, set requests only go to the master, while get requests can be load balanced. So we use the policy field to do that. And the middle box only forwards set requests to our master, and load balances the get request across our 3 slaves. We run the Facebook user workload, and we compare with the vanilla Redis implementation on top of TCP. So the first observation we make here is that even with the random policy, R2P2, because of the DBDK-based implementation and the linear transfer protocol, achieves 5.3 better throughput. And we also have some benefits because of scheduling when we deploy the JBSQ policy. Then we increase the percentage of writes from 0.2 to 2%. And we see that the benefits because of scheduling become more significant. And this is because by increasing the percentage of writes, we increase the service time variability that our servers have. So to conclude, I presented R2P2, a transport protocol specifically for RPCs that exposes the RPC abstraction to the network and enables in-network policy enforcement. By using this new abstraction, we implemented efficient RPC-level load balancing in the network, both on a software middlebox and a hardware programmable switch. And we also implemented a novel JBSQ scheduling policy. Finally, we saw how we can extend R2P2 to support more in-network policies. R2P2 is open source, and we encourage you to fork it and use it. And thank you very much for your attention, and I'm happy to take questions.
All right, we have 4 minutes for questions. If you would, as a courtesy to the speakers, say who you are and where you're from. Thank you.
Hey, I'm Rob Reggie from the University of Utah. One thing I noticed was that in the evaluation you did on Redis, you had a much larger queue size of 20, right? And so I assume there's something about the application that influences what an appropriate queue size is, and I wonder if you could comment on that.
Yeah, that's a great question. Thank you. So the number of outstanding requests that we want to have is highly dependent on the service time that we have on the server. So we want to have enough outstanding requests so that we hide the communication latency between the middlebox and the server. So you can imagine that if you have low service times, you need more outstanding requests. Also, if you have high variability in your service times, again, you need to have more outstanding requests because there will be a gap between very fast requests and very slow requests. So when we're talking about Redis, we have 1 or even sub-microsecond service times. And we also have some sets that are way slower. So in this case, we had to increase, and also the communication latency between our software router and the server is about 12 to 15 microseconds. So because of the service time and the service time variability, we had to increase the number of outstanding requests to get the throughput.
Thank you.
Hi, I'm Zim from MIT. Very good talk, thanks. So I'm just wondering, it looks like you're assuming that clients and server connecting use a single switch, but in the reality, I mean, there are actually many switches between them. So basically, you are trying to make a distributed decision rather than like a centralized decision, right? So what do you think about this?
So can you repeat the question? You assume that the clients can. I didn't
so
get
it's
the
like
question.
in the reality, like clients and in the data center setting, like clients and servers are clienting use many switches. So basically, where to put the information among those switches and who is would be responsible to make this decision, right? It looks like for me that there you basically need to make a distributed decision, right, rather than a centralized decision.
OK, so the design choice that we made here is that we wanted to centralize this decision-making point so that the switch or the middle box has full visibility over what's going on at the servers. This would be way harder to do if you had to make a distributed decision. So the assumption we make here is that each server belongs to one middle box. And for a wider infrastructure, you just deploy different middle boxes, but these middle boxes should not share the servers.
OK, thanks.
Could our next speaker come up and start getting ready while we have this last question?
Mohammed Hedayati from University of Rochester. Very interesting work. I was wondering if, so it seems like you have to track the basically all in-flight RPCs in your middle box to be able to make these decisions. If and this is a lot of state, and if that is, you have identified any scalability issue with that, and what's the maximum throughput that you can get out of your implementation in the middle box?
So the only state that we need to track is the number of outstanding requests per queue. So it's only one number for the number of queues that the middle box is responsible for. In this case, we only had 64 independent queues for our experiments. So this is just 64 independent registers. We didn't try with more queues, but based on the switch characteristics and the memory that's available there, this could scale to even larger numbers. And for practical purposes, I don't think that this would be an issue.
And the maximum throughput that you got out of your implementation?
Sorry?
The throughput that you got out of your implementation, how many RPCs per second?
So the throughput of our implementation was bottlenecked by the server. So we didn't want it to have a bottleneck by the switch. The only bottleneck that we had not at the software middlebox was because of IOPS. So we saturated our 10G links that we had available with tiny packets.
Thank you.
All right, let's thank our speaker again.